So anyway, Jamie,
Yeah.
I spoke to a man called Ben Braam from the Netherlands,
Go on.
and he was heavily involved in the Gaia Project.
Get involved.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
I've got a student called Mardhys Braam who has a very good band who have a single out at the moment on Spotify. It's a band called Mardhys. So you should check that out. I'll put a link in our description. Her dad was heavily involved in the Gaia Project.
Wow.
After speaking to him this morning, essentially he was in charge of this one bit called the BAM, the BAM, which was this way of being able to have this picometer precision. Yeah. And no one thought it was possible, but basically him and his team at TNO solved this problem. And basically meant that Gaia was a go. Go.
Well, I can't wait to hear it.
It's really, really fascinating because it's a lot about Gaia, but it's also a lot about what it takes to be an engineer in the space sector, I think. Having got into the Gaia mission just to talk about it with Ben, I actually can't believe how genius it is.
Yeah.
So I thought even though we've covered it before on the podcast, I thought we'd just do a quick rundown.
Let's do some stats,
pretty
Matt.
awesome, some pretty awesome facts. So it replaces the Hipparcos mission, which ran from 1989 to 93, just basically mapping stars.
Yeah.
So astrometry, which is one of the sort of oldest forms of astronomy, which is basically working out the distance of stars and where they are. So the whole point of the mission is to map stars. So the primary mission objectives is to measure the position and velocity of approximately, get this, 1 billion stars in our own galaxy.
You did that with your little finger against your mouth, didn't you?
I totally did.
Yeah.
Just so you know, that's only 1% of the stars in the Milky Way.
There's a few of them, isn't there?
And so Gaia observes 1 billion stars 70 times each over 5 years. So that's 40 million stars a day it's observing, right?
You're going to hurt my head again with this, aren't you?
And it slowly spins and sort of takes a picture of all these stars and basically, because it does it over 5 years and it has this absolutely insane precision, it can see how they've moved so that it can work out how far, from parallax error, how far away they are, but also how they're moving as well.
I love that stat that it's only 1% of the stars populating Milky Way.
Is 1 billion.
1%.
I know. And 99% of that 1 billion that Gaia will observe have never had their distances measured accurately before. It's got the largest digital camera ever taken into space. So that's a 1 billion pixel camera. So your smartphone is about 10 million pixels. That's a 1 billion pixel camera.
That's pretty clear.
It's a pretty ridiculous camera. But this is the most amazing thing. So for objects that are 4,000 times fainter than the naked eye limit, in other words, stars that you couldn't possibly see, Gaia can measure their position to an accuracy of 20 micro arc seconds. Now, that is like looking at a human hair at a distance of 1,000 kilometres.
Oh, God, that's nuts.
It's absolutely insane. And this is why they needed this pico precision. That's 12 noughts of a meter. That's a millimeter is 3 noughts past the decimal place. 12 noughts past the decimal place is pico precision, and so it has to be absolutely ludicrously robust, the data. But the data coming off Gaia is insane. Obviously, it's spinning around and taking billions of stars with all this data. Now the data set is already 30 times bigger than the whole of Wikipedia.
My God. Matt, you've made my nose bleed.
It's absolutely insane, isn't it? But it's not just stars. It's not even just stars that it's picking up. It's getting their brightness and temperature and composition and all those sort of things as well, by the way. So eventually it'll create this 3-dimensional map of the galaxy. And they've actually released the first colour 3D map of the galaxy very, very recently on August 16th.
Where can people see that?
Just go to the ESA website and go to the Gaia page, because it's a fantastic mission. There's some really brilliant bits. There's an article that's just come out about how this data set is so enormous they're having to use really, really novel methods to sort of go through and look at it. So they've used things like software that mimics the human brain. And that's already found 6 stars that are zipping from the centre of the galaxy right out to the outskirts at super high speeds and things like that. And so, it's such a brilliant sight. But a brilliant thing about it is it not only is it finding all these stars, it's finding hundreds of thousands of asteroids and comets. So Debbie Lewis will be happy about that.
She's happy.
Yeah, there'll be 7,000 planets beyond our solar system. I don't know why they put beyond our solar system, because it's not like it's going to find 7,000 planets that we haven't noticed within our solar system. That would be ridiculous. It's going to find tens of thousands of brown dwarfs, or failed stars as some people call them, 20,000 supernovae.
What?
And hundreds of thousands of distant active galaxies, quasars. So, I mean, that's pretty cool, isn't it? And it's even taken images of the Triangulum galaxy, for example, Messier Object 33, and it can pick out individual stars in other galaxies. That's how absolutely insanely accurate this little satellite
Well, for one, Matt, I'm going to go on the ESA website and check that out as soon as this podcast finishes, because I haven't seen that yet.
You can even start looking up things like Lissajous type orbits around L2. So this thing is doing a kind of orbit around Lagrange point 2, which is the other side of Earth to the moon. No, to the sun. It's a Sun-Earth Lagrange point 2.
Well, Matt, you know that's the kind of stuff I do, but please don't advertise it on the podcast, I'm trying to get some friends here.
You can get super geeky, or you can just look at the pictures and go, wow, that's amazing.
Exactly. You choose your own path.
You can choose your own path.
Beautiful.
As Fleetwood Mac once sang.
What a tune.
More about the Gaia mission and more about the BARM. Really fascinating stuff. I'm joined by Ben Braam, who was an engineer on the Gaia space mission. Hi, Ben.
Hi, Matt. This is my first interview, so I'm an amateur. So.
I'm an amateur interviewer, so don't worry. Tell me a bit about yourself and how you got into space would be a really good place to start.
Yeah, that is a very long story, but I will do the short one. I was working at a technical university in the early 80s. There were economically very difficult times in the Netherlands, so I had to find another job. And there was a vacancy at TNO for a program which was called ISO Short Wave Spectrometer. It's a very well-known program in the context of ESA. And they needed a mechanical engineer for that. And in my working times at the university, I had developed an aluminum magnet. So everybody says that cannot be. It's possible, and those systems are available on the market nowadays for separation of mostly aluminum from waste. So you could it's a rotating magnet system, and you induce eddy currents in aluminum, and then you shoot them out with a very high speed, and so that was quite a spectacular result and a good basis for my solicitation at TNO. So I was lucky. I got in, and directly in the space program, and I had no idea about space, nothing at all. And also there were a lot of other things happening. It was a time of the computer-aided design systems which had to be used. ESA was getting more professional. That means you had to make a finite element model of everything that you had done and had to be tested. You needed to do extensive calculations, thermal calculations, mechanical calculations. And I just started that. I had to. And we built a shortwave spectrometer at TNO together with a group in the Netherlands called ESROM. They are the scientific part for the science programs for space in the Netherlands. And it was done it was a block of aluminum, and there were lenses and in it in the system to have it as stable as possible. And because it was in the infrared, it could be done directly by machining in the block of aluminum, which was. So that was really my first experience. It was a very successful program, launched, etc., in orbit for many years. And really that was also a sort of start, because it had to be done by machining. You couldn't do things at a micrometer level. So, and what is a micrometer? You push against the wall and it goes, depends on where you are, a few micrometers. So that was really something at that time at the edge of what was technically possible. That was a direct link. And then of course you had optics, and you know optics, you polish the last atoms, and then you have a surface for your glasses that can be used. But direct systems for making things at nanometer level, which you need in optics, really didn't exist at the moment. Also, shortly after the shortwave spectrometer for ISO, I designed the grating box for XMM. And I have done that in silicon carbide. I found a paper, it was from an English guy, Chetwynd or so, in precision engineering, and he had made a sort of scheme that you could choose the best material for the system that you wanted to design. And it ended to be silicon carbide, and which was was a material, it existed. And later it was used extensively also in electronics and for many applications. But at that time it was very new. So I designed it, but in the end the program decided, because it was an ESA-NASA program, that the grating box, have any idea what a grating box is? You have the telescope, and the XMM is a Röntgen telescope. Right. And then the beams go to the grating box and then to the detector. And in the grating box, you get these angular separations based on the wavelengths of the incoming radiation. So I designed it, but the decision was made that it should go to NASA, and they did it at Lawrence Livermore in the end. And I remember, because I still had contacts for questions by the people from ESA, and the first message came back when the Americans started, those Europeans, they have made such a bad design. How can you do it? And then, they start to do their calculations, and they ended up with a silicon carbide grating box in the end, because it was the only solution that could be really realized for such a system. So I heard that many times. So this is a really fun situation, because at that time I was still an amateur, so I just started this space business, and then you get in these things. And the next step was really that I made in my career. Also for the big line, I started engineering, but I grew more and more to business development. So, and first time only engineering, then combining, and the last 10, 15 years mostly. So in the Gaia times I was really a business developer already, but heavily involved in the program, of course. But anyway, we made a step from micrometers to nanometers in mechanical systems. And we had a program running, and it was then called, it was for the Aristoteles mission. And it was later replaced by GOES. It was Earth observation for gravity, not for gravity wave detection, but for gravity measurements. Yeah. And in Aristoteles, this satellite needed to be calibrated, and it had to be done by shaking a mass of about a kilogram over 6 millimeters with a lateral deviation of 15 nanometers. And we couldn't handle, the people who were working on the program couldn't handle it. So I went to my boss and I said, there was Roel Hoekstra at that time, quite a famous guy in the Netherlands. And I said, Roel, I will solve the problem. I had no idea how to do it. But anyway, I went to people, talked to them, and what could be, who are the people really, because something like that had never been done in the world. So you have to start from zero and really get the best people to do it, because that is really the fun part. You can do this work only with the best people in the world, otherwise you will never succeed. So you'll have to find them. And I ended up at Rien Koster. He was at that time a professor. He's retired now for many years already. He was professor at the University of Twente in Enschede, the Netherlands. I don't know if you... It's in the east of the Netherlands. Wow. Anyway, I ended up there and talked to him, and he said, okay, we are going to solve the problem, but then one of my students has to graduate on this topic. Which you never do. It's such if I think about it now, this is an entirely crazy step. You are not going to solve the most difficult problems with students. But okay, Rien was on the back. Rien was on the back, and it worked out. We made a very special design, which is still going around in this world of mechanical engineering, because it's. Rien has made a book with all his designs, and he's very good in describing them, so they need a third of a page, half a page. This one needs 6 pages to really understand how it works. Yeah. And then it was, you had to move it, and we had a very special arrangement of flexures to keep it along the linear track. And also, you have the gravity effects, you have all the problems that you have on Earth, vibrations from so that was really, so that was a big step, and of course it was very successful also, and we could show it to the world, so to say. It was a pity that the program was not continued. But then also, and then there was the next step, and we got to the picometer level, and that was in the 90s. At that time, I could go to ESTEC like I wanted. I could get in, talk to people. Now it's much more difficult. It's much more stringent, organized, and so I knew a lot of people who were really at the core of the programs. And one of my favorites, because he was very open on everything and very much involved in many programs, was Philippe Roussel. He was a Frenchman, retired already. And before Gaia, I did many programs with him, mostly in space interferometry. For instance, we did the first optomechanical setups for interferometry in space. And we developed, I don't know if you are familiar with the Darwin program, which is not alive anymore. It stopped in 2007, but it was a program with 5 free-flying satellites for detecting exoplanets. And then everything had to be at nano-level mechanics again. And we did a lot of it at those stages. We made delay lines. I don't know what the delay line is, but Anyway, the light comes from a star, goes to your detector, and then it goes to several several directions. It goes to a satellite, second satellite, but the light has to combine again. So how do you do that? And you do that with a delay line. So we developed the first delay lines at just for a test setup to demonstrate it could work, and also we developed delay lines how they should work in space, and they are now going to be used in other programs because it's an existing technology. So
you use that for multiple satellite?
For multiple satellite systems, because we also developed the delay lines for the ESO VLTI. You know the ESO program. That's the European Space Observatory.
Yeah,
and they have the telescopes in Paranal in Chile.
The ones that discovered the TRAPPIST system.
Yeah. So we developed the delay lines and several systems also for the ESO VLTI. Anyway, I knew those guys at Aztec, and one day I saw Philippe in the cafeteria in the restaurant, and he came to me and said, "Ben, we have got something. They are going to call it Gaia, and it has to work at a picometer level." I said, "Okay, we are going to do it," and because that is my attitude. And
so pico, how many zeros after the?
12.
12. So that's
12. So it's about hundredths of a atom diameter, something like that.
That's small.
So I don't know. It was you can see a coin of 5 millimeter at the moon. If that would be an optical system. So anyway, Philippe came to me in the restaurant and he said, and okay, an ITT came out a year later or so, and so we decided to make a proposal because that is what TNO is for. We are supposed to do in the Netherlands the things that have not been done before, because that is so. I wrote a proposal myself with others, of course. In this work, you always work with 10, 20, 100 people. It depends, of course, on the size of the program and the length. But you work with a lot of people. I made a proposal with two colleagues, Bart Snijders and Peter Kappelhoff. And when I started, I thought, okay, this is really crazy. This is not possible. But we started thinking about it, I got the inputs, and at the end, okay, it's possible. And we made a proposal, and we won the contract. And we demonstrated that you could really measure picometers because that was in itself not so special, because that was done for those gravity programs like LIGO and Virgo. But not in a relatively simple setup that could be launched in space.
Did that change because the one thing that I did spot was that Gaia was an acronym for a particular type of interferometry. And it no longer stands. They've just kept the name Gaia because they've actually changed the method of how Gaia actually works. Was it at that point that it changed, or
no? It was This concept of Gaia, it came from people I knew very well was called Astrium in Toulouse. Right. People like Frédéric Saffat, Bertrand Canvel, they were really geniuses in designing satellite systems. And they developed the concept of Gaia. But the possibility of measuring picometers was entirely open at that moment. So ESA came out with this ITT because that was the go-no-go for the program. Okay, we started working on it. We had all the confidence that it would work, and it did work. Also a relatively simple system, only we had to do things otherwise. We had made normally you have a vacuum chamber where you put your system in, and it's a sort of cylinder type of system. And we had to make a square box where we could lift off one side with special tools because it was extremely heavy, and vibration reduction system specially designed, etc., etc. And also, and we had to do it like that because the taking off, because the alignment of the optical elements was very delicate. So people had to be free moving. If you are in a cylinder and you go in, you can understand that that's not so easy. So we had to do a lot of new developments, and we were successful. We could measure it, demonstrated it. So at that moment we were very popular because it was the go for the Gaia program, and we came for a final presentation to ESTEC, which is not far from us.
So can I just to put it in context, so the reason why you had to have this level of accuracy, this picometer accuracy, is that Gaia is mapping stars using the parallax.
Yes, yes.
And obviously when objects are a very long way away, they don't move very much.
No.
So you have to kind of have something that's incredibly accurate. I heard that it could measure the width of a human hair from 1,000 kilometers.
Yes.
I mean, that for me just blows my... It's just mind-blowing.
But the point is the satellite system has to be stable at picometer level. Yeah. That is the difficult part. And what we did, that is really a metrology system that can measure the stability. So, and if you can measure the stability, then you can correct for errors. Because a satellite system is not completely stable, because you have outgassing, you have the sun heat up, and you have to cool down. It's extremely difficult to make it stable.
So the real skill in there is the way that it's always calibrating, it's always looking at itself and then self-correcting. So that's really the mechanism that's going on, right? Okay.
That's the part that it's a metrology system, as we call it, which monitors the stability, and then you can correct the data that you get down on the Earth after the measurements.
And that's a lot of data, isn't it? I mean, the data that comes off Gaia just seems to be
that's
a ton of data.
That's organized now by a lot of people in Europe, but the main players are in Leiden. They are from the Leiden Observatory, and over the years I knew those guys very well. Anthony Brown is now in charge of the data handling of the.
So this no-go, let's go situation, what sort of year were we talking about then?
About 99, 2000 or so, something like that.
Yeah. And it took off. When did Gaia take off?
For the mission design. Oh, the launch in 2013.
Right. Okay.
It was December 2013.
Did you go to the launch? Or?
Yes. At ESTEC. But there was really a big happening there. Yeah. So. And that's amazing, because you at those moments you walk 1 meter above the normal floor level, because you have contributed something very special to the program. And if you look at the websites of ESA, then you get an impression of how important the BAM, that you call it, the Basic Angle Monitoring System, was for the program. Because when it was delivered to ESA, you see especially photos made and things like that.
Yeah. So so that the system that you developed, this self-correcting thing, is called the BAM.
BAM, Basic Angle Monitoring System. Yeah.
Right. Yeah. And so that's obviously that's a pretty. Is it something that is going to be used on other satellites, or was it purely made for that kind of, or variations of it, or is it?
It was purely made for Gaia, but what you have done, you have made a step in technology, and now it's possible to make the system also for other applications, because you see people want more and more special. So because the development of the BAM, we did that first program, which was called another name, OPD Test Bench, but the BAM itself, it was a huge program for TNO with many people. And we had to make so many technology steps to do that. We had to learn to polish silicon carbide mirrors in a very special shape. And if you have silicon carbide, it's very fragile. If you do this, it breaks. So you have to make a very complex camera system, optomechanical system, of very fragile material. The only thing that you can do is put pressure on it. And that's practically infinite, doesn't exist. But you can, so joining the different components is possible, but still very difficult, because you have seen an impression of the bench. There are many components on it, glass components, silicon carbide components. You need to inject a laser in it.
So what was the main worry with the vibrations of launch? Is that really the hard thing to overcome, or is it more the calibration in space? Or both hard?
Yeah, the hardest in the program was not the vibration, was really developing all those elements to make the system complete, because you had to implement glass component on this optical bench and still maintain this picometer stability. That's never been done. How are you going to do that? Yeah. So we had to invent new schemes of design, optical, mechanical, to do that. Also, we had to join components, and we needed special screws where you could tune the torque that you induce in the material, that you know what you are doing. And then the alignment was very difficult, because you have to put an optical element in a certain position, and you could only do it with silicon carbide shims. So you have to put a material between it, which is exactly of the good shape that you need to put the things together. So and of course a lot of it you knew in advance, but most of it came on doing the work. That was very challenging. And I think that the people that have worked on it, they were really amazing. It was really a part of their life for a year. They did nothing else.
So at TNO, how many people were working on the BAM?
At six people full time. But then you had a lot of other people like quality management, project management. So,
but 6 serious engineers and
they really were the core of the team. Yes. Yeah.
So I mean, it's amazing, isn't it? Particularly, it's something that goes unnoticed. I think with ESA in particular have got some amazing satellites up in space, on orbit and all these bizarre. I mean, because Gaia itself is in a orbit. I can't remember the name of it now.
L2.
It's at L2, but it's doing, what's the name of it? It's got a certain type of orbit around L2, but ESA have got all these different craft, and the effort and all the technology that goes into making these things is absolutely incredible. But because we don't hear much about Gaia, even though it's a European project, you'd think that we'd hear, because it's the first lot of data with has been absolutely
released. But the next data release, I looked. I think it's in April 2018. Right. Because they have to do so much work calculations before you cannot just release the data.
It's generated something like 30 times the size of Wikipedia in data at the moment, and that's including all images and everything else. And I'm thinking, oh my gosh, that's a lot of data to get through. So I mean, presumably that's one of the hardest parts of the project, is actually the crunching of the data.
Yes, certainly. Yes.
there was one thing that does interest me is that whole personal voyage of being involved in a space project, because these space projects last a long time. There's a lot of build up to them, like you said. That Gaia was already on the table, and you got involved in 1999. It doesn't launch till 2013, and then it's going to be another 10 years till we see the work finished. So these things are lifetime projects. So can you give us a bit of insight into how that feels to be part of these projects that last a long time?
For me, because I was last 15 years I was also a business developer, so I was involved in many projects, Darwin, ESO programs. I did all the work for TNO, Gaia, of course, many more. So for me personally, it was not so special because there was so much to do. And also for TNO, it's quite the group of people that I was in. We always did really long-term programs. Also for ASML, wafer stepping technology, which it's also about nanometers and below. So we had an organization who was quite used to that approach in programs. So it was for us, it was not so special. But I can imagine if you are a scientist and you have an instrument developed, and you have students coming in and going out, and how to keep it alive at a university, I think that is much more difficult. And because it goes really beyond your normal practice as a professor at a university. You have a position of education, but I've met many of those people, and it seemed for them, as I looked at it, quite normal. To behave in that area. And maybe the last story then, it's about Gaia. It was launched in 2013, December, and then it had a very long commissioning time, and it also had to do that there were a lot of effects we were not well enough understood. And it had to do with heating, cool down. Then people start to blame. And the problem was with the BAM system. That was the general opinion, especially at Matra, which is now Airbus. The BAM system is jeopardizing. But then, at a certain moment, someone at ESTEC said, okay, but let's assume that the BAM is working good, and the rest is not so good as it is supposed to work. And then everything fell in place, because it was, and then all the data were understood, and so the whole program changed. And I was already retired, but I got a phone call. People of ESTEC are coming to TNO for a celebration that BAM has saved the Gaia program. So that was really.
Wow. So that's before it launched?
No, that was after launch.
After launch, they had some problems, and they wondered what was causing it.
Exactly.
Was that the escaping light problem, or stray light problem?
Stray light. There were many problems. Yes. Yeah. And so that's look. BAM was for saving the program, because it was for correcting errors in the system. So it really did do that, and also in the end worked much better than everybody thought, because it had to work at, I think, 15 picometers, but it worked at 0.3 picometers or so, something like that. So people from ESTEC, Dominique Doyle and others, they came specially to TNO, and they invited me, and after that there were 2 more celebrations for the successes.
That sounds like it's. Everyone was pretty happy then.
Yeah.
Everyone was.
Certainly. You're like a little boy who scored a goal in football.
Well, I mean, it certainly seems like a really, really important mission. I mean, it seems to have like this kind of, not just as it mapping stars, but it's mapping quasars and asteroids and even exoplanets as well.
Also, and who knows what else will be discovered there? Because if you know, it measures the position of stars, so you know how they move during the time of observation. but also you can calculate back where it came from.
Yeah. It's even managed to sort of capture things like the Triangulum galaxy and pinpoint stars in another galaxy, which I think is pretty incredible stuff.
Yeah, those scientists, they have, this is a work of a big group of people. Yeah. We had many technology development programs. We had connections with the Technical University in Eindhoven, and so many things were done in preparation and working together and coming up with new, and then you had to find a supplier who could this, and so there's so much to do.
Yeah, it's really fascinating. Yeah, brilliant. Thank you very much. Thank you very much. That's perfect. The Interplanetary Podcast, putting the ace back into space. Just as the last thing on the podcast, Jamie, that we should really talk about, because it was a big thing, wasn't it? Let's face it. Was the American eclipse.
The solar eclipse.
Do you know what was really annoying about the solar eclipse, other than the fact that I didn't get to see it, which was pretty annoying, was how rubbish the BBC coverage of it was.
Yeah, really not good, was it?
Well, the amount of times they sort of, like the news headline, the first total eclipse in 100 years. It's like, are you having a laugh?
Yeah, that's a joke.
It's like, I know it's not, because there was one in Britain like 10 years ago. It's like, for goodness sake. So it was just, it was a bit crazy. It was just really annoying me. What they actually meant to say was it was the first one that went through the whole of America, so that
the American one.
It went coast to coast, and that's the first time that's happened for a very long time.
You know what? I think it was really nice that it was America, because they've been having a bit of a hard time of late, haven't they? There's a little bit of light relief for them.
Oh, my word. Did you see Trump going out to look at the eclipse?
I did. You know what? As much of a buffoon as he absolutely is, you know that there was a camera guy just waiting for the moment he took off his glasses, which he was wearing. But the second he looked, it was like, oh, you idiot. And surely he must know now that he can't put a foot wrong.
No.
Or he's going to get eaten up. And I'm all for that.
Oh,
because he is an idiot.
So everyone in the whole of the USA could see at least a partial eclipse. So
amazing.
It's
Did you see the one from the air? Somebody took from the air.
Oh yeah, the ones from
beautiful.
The ones from the plane. Yeah, absolutely incredible.
Really lovely.
I love the fact that you could see the shadow going from either side of the plane. It was really amazing, wasn't it?
Yeah, incredible.
Yeah,
incredible scenes.
Yeah, there was an article.
When's the next one, Matt? I really want to go to one.
Well, there's another great American eclipse, sort of going slightly the other way in 24. So it might be worth going over and checking that out.
We should do that.
So, it's sort of going to come hot on the heels. And there's one place, and I can't remember where it is, that gets it twice, essentially totality twice in this time round and in 24. But this one goes on a slightly different route.
When's the next one in the UK? Can we predict that?
Oh, I don't know. It is definitely predictable, but I don't know when it is. It's a long time away. I don't think it's in our lifetime, in fact.
Well, you know who we should ask, Matt, don't you?
Who?
Our avid listeners.
Yes. Oh my gosh, this is becoming the theme of the show.
I tell you what the amount of homework people have got, it's incredible.
Yeah, absolutely. In fact, I tell you what, I'd really like to hear your eclipse stories as well.
Yeah, please do, because we had some of our podcast buddies send us in pictures of them, all hanging out in their glasses. We were a bit jealous, weren't we, Matt?
Oh, jealousy actually doesn't really cover it, to be honest.
Whilst we were happy for them, we were also very annoyed, weren't we?
Yeah. So I've been listening to, obviously, some of the other podcasters, all of the podcasters that are talking about it, and it's...
It's like when your mates go away to the Caribbean and you're stuck in Grimsby in a rainy office or something. You know what I mean?
Yeah, and you can tell by their little enthusiastic voices that it really was essentially almost a life-changing event.
It's pretty spiritual.
Yeah. So not while we've been away, it has been a pretty exciting time in space launching as well.
It has.
We've had one that we've never had on the show before. Quite recently, called the Minotaur. The Minotaur 4. Yeah, that flew from Cape Canaveral the other day. In
Now,
fact,
am I right in thinking a minotaur is the head of
a man,
a
a bull.
bull and the body of a stag? Is it?
Oh, not a stag, a donkey, horse bull type man.
Horse, bull, donkey, stag.
It's something like that. But in this case, it wasn't one of those, Jamie. It was actually a rocket.
Blimey.
Yeah, but you don't often see that one, do you? And
No, you really don't.
And we had.
Where was that from?
That was from Cape Canaveral in Florida.
Matt, I've just looked up what a minotaur is. In Greek mythology, the minotaur was a creature with the head of a bull
Yeah.
and the body of a man, or, as described by the Roman poet Ovid, of being part man. And what do you think it is, Matt?
Stag with hooves?
No, part man and part bull.
Oh.
So there we go. That's it. Part man, part bull.
Minotaur.
I thought it was.
Aren't you part man,
I thought it
part
was the thing
bull?
in the. It's only when I see a red rag.
This podcast feels a little bit like part man, part bull. Sometimes.
Yeah, that's true. Yeah.
No, it doesn't really.
There's a lot of bull.
There's a lot of fact checking in the editing process. Let me tell you, Jamie.
Yeah, that's true. Yeah.
So and SpaceX managed to do yet another a Falcon 9 launch that landed successfully.
Ticking him off, isn't he?
No, so that I think has now he's overtaken Russia.
Because we were worried for a while last year, weren't we, about old Musk and just a series of failures.
Yeah, and
but
and also there was the other SpaceX launch which was a resupply mission to the ISS. That was back in early August or mid-August, actually. I mean, there's been loads. There's been an Atlas V. There's been the Japanese H2A. There's been the Vega rocket's gone up. A Soyuz has gone up, and it's just been never-ending rockets. And I have to say, September is looking extremely busy.
It's looking busy, is it?
Yeah.
Matt, did you see Elon Musk's Hyperloop video this morning?
No, I didn't see Elon Musk's Hyperloop video this morning.
Go to his Instagram page and check it out. 200 miles an hour underneath Los Angeles that's being built.
I'm super dubious about Hyperloop.
Why?
It's because... Have you ever seen those YouTube videos called... what's it called? By Thunderfoot. Hyperloop Debunked. You should watch it.
Oh, really? I'll have to check them out. I'm not aware of them.
Yeah.
Well, it's been a pleasure talking to you again about space and bull.